And in the preceding sections, we have dissected the internal alchemy of the Raptor 3, the high-pressure combustion, the full-flow staged cycle, and the molecular efficiency of the methane-oxygen bond. However, in the unforgiving physics of propulsion, having a chamber full of high-pressure gas is not the same thing as having a rocket engine. Without a method to direct that energy, a combustion chamber is simply a bomb. To transform chaotic, multidirectional thermal energy into the linear, purposeful force we call thrust, we require a masterpiece of geometric engineering, the nozzle. And if the combustion chamber is the engine's processor, where the raw data of propellant is computed into energy, the nozzle is the output formatter. It is the final stage of the pipeline, where the abstract potential of high-pressure gas is rendered into the physical reality of momentum. In this section, we will explore the math of the bell, the sophisticated fluid dynamics that allow the Raptor 3 to focus a scattered whisper of molecular vibration into a directed shout of cosmic proportions. In the geometric transformation of energy to understand the nozzle, one must first understand the state of the gas as it exits the combustion chamber. At 350 bar of pressure, the gas molecules are in a state of violent, isotropic agitation. They are colliding with one another and the walls of the chamber billions of times per second, exerting force in every direction simultaneously. This is static pressure. In its current state, it is useless for propulsion because the forces acting on the left wall of the chamber perfectly cancel out the forces acting on the right wall. In Newton's third law for every action, there is an equal and opposite reaction dictates that to move the rocket up, we must move mass down. The nozzle's primary function is to act as a transducer. It converts the random thermal energy of the gas, specifically temperature and static pressure, into directed kinetic energy, which is velocity. And imagine a crowd of people in a large hall, all pushing against one another in a frantic, unorganized crush. This is the combustion chamber. Now imagine a single narrow exit opens, leading into a long, widening corridor. As the crowd funnels through the exit and into the corridor, their random jostling is forced into a single direction. They begin to run. The pressure of the crowd decreases as they gain velocity in one specific vector. This is exactly what the Raptor 3 nozzle does to the exhaust products of methane combustion. In the convergent-divergent logic, the de Laval effect, the Raptor 3 utilizes a convergent-divergent de Laval nozzle. This shape, a narrowing throat followed by a widening bell, is not a stylistic choice. It is a mathematical necessity dictated by the compressible flow of gases. And as the high-pressure gas moves from the combustion chamber toward the throat, the narrowest point of the engine, it accelerates. According to Bernoulli's principle, as the area decreases, the velocity must increase to maintain the same mass flow rate. However, there is a physical limit to this acceleration in a converging duct, the speed of sound, Mach 1. At the throat, the gas becomes choked. It cannot move any faster through that narrow opening regardless of how much pressure you apply from behind. And for a computer science professional, think of the throat as the system bus width. It represents the maximum bandwidth of the hardware. No matter how fast your software or combustion is, you can only push so many bits or molecules through the bus per clock cycle. And however, a strange thing happens once the gas passes the throat and enters the divergent section, the widening bell. In subsonic flow, a widening pipe slows gas down. But in supersonic flow, a widening pipe actually speeds gas up. Because the gas is under such immense pressure, it wants to expand. As the nozzle walls move away from the center, the gas expands to fill the space, and that expansion energy is converted into further longitudinal velocity. By the time the exhaust leaves the rim of the Raptor 3 nozzle, it is traveling at many times the speed of sound. In the nozzle as a renderer of thrust. In the language of software engineering, the nozzle can be viewed as a renderer or an output buffer. The combustion chamber provides the raw data, a high-entropy set of values representing heat and pressure. The nozzle takes this raw data and applies a geometric shader to it. And if the nozzle is shaped incorrectly, you get artifacting. If the bell is too short, the gas exits while it still has high internal pressure. It overspills the edges, and you lose potential velocity. This is like a memory leak, where energy that could have been used for thrust is instead dissipated into the environment. If the nozzle is too long or incorrectly curved, the ambient atmosphere can push back against the exhaust, causing flow separation, a catastrophic error state where the exhaust stream becomes turbulent and can even vibrate the engine to pieces. In the math of the bell is the optimization algorithm that ensures the final product. The exhaust stream is perfectly formatted for the environment, whether that is the atmosphere or the vacuum. The goal is to reach the exit plane of the nozzle with the exhaust pressure exactly equal to the ambient pressure. When these two pressures are balanced, the engine is perfectly expanded and its efficiency is at its theoretical maximum. In the atmospheric interface, the balloon model, the primary challenge for the Raptor 3 is that it must operate in two completely different operating systems, the thick, high-pressure atmosphere of Earth and the zero-pressure vacuum of space. And to visualize why this matters, use the mental model of a balloon. If you inflate a balloon at sea level, the air pressure outside the balloon pushes against the rubber, keeping it a certain size. As you take that balloon higher into the atmosphere, the external pressure drops. The air inside the balloon now has less resistance, so it expands, stretching the rubber further. And the exhaust of a rocket behaves exactly like that balloon. At sea level, the heavy atmosphere acts as a wall of pressure. It squeezes the exhaust stream, preventing it from expanding outward. To counter this, sea-level engines, like those on the Super Heavy booster, have relatively small nozzles. In the vacuum, there is no atmospheric pressure to hold the exhaust in. As soon as the gas leaves the nozzle, it wants to spray out in a 180-degree arc. Any gas that moves sideways is wasted energy. It does not contribute to the forward-upward momentum. And this is why the Raptor Vacuum, or RVac, variant looks so different from the standard Raptor 3. The RVac has a massive, elongated nozzle extension. This larger bell acts as a guide, forcing the gas to keep expanding against the nozzle walls for as long as possible, extracting every last bit of directional velocity before the gas is released into the void. And in computer science terms, the sea-level Raptor is a mobile-optimized version of the code, built for a constrained, high-latency environment. The RVac is the server-side version, unconstrained, high-throughput, and designed for maximum performance where resources like space are infinite. And vectoring and directional control, the invisible hand. The nozzle does more than just provide efficiency, it provides control. By tilting the entire engine assembly, a process known as gimbaling the Raptor 3 changes the vector of its thrust. And however, the physics of this are governed by the nozzle's geometry. Because the exhaust is moving at supersonic speeds, it possesses immense stiffness or momentum. Redirecting this flow is like trying to bend a steel rod. The Raptor 3 uses high-pressure hydraulic or electric actuators to tilt the engine, but the math of the bell ensures that even when tilted, the flow remains laminar and attached to the nozzle walls. And if the flow were to detach during a gimbal maneuver, the rocket would experience a sudden drop in thrust and a torque spike, likely leading to a system crash or loss of mission. The precision with which the Raptor 3 nozzle is machined allows for sub-millisecond latency in thrust response, giving Starship the agility of a much smaller vehicle. And material science, the thermal interface. The nozzle is the most thermally stressed component of the engine. While the combustion chamber handles the highest pressure, the nozzle handles the highest flux of heat over a massive surface area. And to prevent the bell from melting into a puddle of superheated alloy, SpaceX utilizes regenerative cooling. The nozzle is not just a sheet of metal, it is a complex heat exchanger. It is honeycombed with thousands of small cooling channels through which cryogenic methane flows before it ever reaches the combustion chamber. And for the computer science reader, this is the hardware equivalent of active liquid cooling in a high-end GPU. The waste heat generated by the processing or combustion is captured by the coolant, which is methane. This serves a dual purpose. It protects the hardware, specifically the nozzle structure. It prefetches energy. By heating the methane before it is burned, the engine increases the initial enthalpy of the fuel, making the subsequent combustion even more efficient. And it is a closed-loop system, where thermal noise is recycled into signal. The spaghetti versus the sculpture. And when we look at the evolution of the Raptor nozzle from the early prototypes to the Raptor 3, we see a move toward integrated design. Early versions of the engine were covered in a spaghetti of external plumbing, including sensors, wires, and cooling lines wrapped around the bell like an unfinished circuit board. And the Raptor 3, by contrast, looks like a sculpture. Much of the plumbing has been internalized or refactored into the structure of the engine itself. This is not just for aesthetics. It reduces the attack surface for potential failures. In the same way that a clean, well-refactored codebase is easier to maintain and less prone to bugs, a clean engine nozzle is more resilient to the extreme vibrations and thermal stresses of launch. In the limit of the bell, why we can't go further, one might ask. Why not just make the nozzle infinitely large to get infinite ISP in a vacuum? And the answer lies in the law of diminishing returns. As the nozzle grows, its weight increases. Eventually, the mass penalty of the extra metal outweighs the thrust gain from the extra expansion. Furthermore, a nozzle that is too large becomes a sail in the atmosphere, creating immense drag during the early stages of flight. And the Raptor 3 nozzle represents the global optimum of this multivariable equation. It is the perfect balance of weight, heat dissipation, expansion ratio, and structural integrity. It is the point where the math of fluid dynamics meets the reality of material science. In conclusion, the interface of power. The nozzle is the final interface between the machine and the universe. It is the point where the internal logic of the Raptor 3, the methane, the 350 bar of pressure, the full flow cycle finally touches the external world. And without the math of the bell, the Raptor 3 would be nothing more than a very expensive heater. With it, it becomes a literal engine of change, capable of pushing humanity toward the stars. The nozzle takes the chaos of fire and formats it into the order of momentum. It is the lens that focuses the light of combustion into the laser of thrust. But as refined as the Raptor 3 is today, it didn't emerge from the vacuum of design as a finished product. To appreciate the sleek, refactored beauty of the current engine, we must go back to the beginning, to the era of technical debt, spaghetti code, and the raw, unpolished ambition of the first prototypes. In Section Break, Raptor number 1, the spaghetti prototype.